About eStitch, top-down library learning for eGraphs, and this is some work that I did with my colleague Maddy and our advisor Armando Solar-Lezama. And to get started, what is library learning? So the idea here is that code is often quite repetitive, and we can find common structure within it and write a library function that kind of generalizes out that common structure. This is a very common problem that shows up in a variety of different programming languages tasks. For example, program synthesis, you might want to have a shorter overall program that you're trying to generate, and library functions help shorten it, which is helpful. You might want to clean up some code that was written by humans and make it smaller so that it satisfies the don't repeat yourself principle, etc. You might want to discover concepts. For example, if these programs are coming from some kind of a symbolic regression on data or something like that, it might be an important part of your process. And of course, it's useful in a variety of compiler tasks. For example, in decompilation, you might want to be able to pull out library functions from assembly code. And here, we're looking at one particular abstraction, and this represents regular polygons. That's what's going on in the background. And if we rewrite the corpus here to use this library of one function, we end up with a much smaller corpus that is potentially easier to understand if you were to translate these all into human-readable tokens. And so, in general, library learning is the process of starting with some corpus. Here, we've got these two programs, and you've got some common structure. And you have that this structure matches at a particular set of locations in the corpus. So here, for example, the common structure is this +2 square root thing, where the square root has some variable, and that variable is unique to each location. And we can rewrite this, so each location gets rewritten to a function call. And this results in the corpus being overall smaller, which is our goal. There's two important pieces of prior work in this space. One of them is Stitch, which is a top-down branch and bound algorithm that is very fast, and it finds these abstractions quickly. But it can't handle rewrites. So it can't handle, plus AB is the same as plus BA. It operates over program trees and doesn't really take into account saturation, equality saturation. Babble, on the other hand, is the other important piece of prior work, and it is useful in that it is eGraph native. So it works by anti-unifying pairs of E-classes together. And as a result, it handles rewrites very easily. However, it's a bit slow. It has a quadratic complexity. And so it's taking minutes on kind of mid-sized problems that Stitch would be able to solve quite quickly, even though it's solving them incompletely. So our question here is, what if we did Stitch, but over eGraphs, right? So then we get the best of both worlds. So just as a quick outline of this talk, first we're going to have our problem statement, then we'll talk about Stitch, then our approach, and then some experimental results. So the formal problem statement here is that we want to find some abstraction f that compresses the corpus p. And effectively, the cost function that we're trying to minimize here is the size of the rewritten corpus plus the size of the abstraction. We add in the size of the abstraction, otherwise the most compressive abstraction would just be the min term of the entire corpus, and then that's just like one big abstraction. Obviously, we don't want that. And so the overall number that we're actually going to report most of the time is the original cost of the overall corpus divided by our cost function. So effectively, if you start out with 100 tokens and you end up with 50, that's a compression of 2x. That's kind of a more interpretable metric. And so now that brings us to the most important piece of prior work, Stitch. Stitch is a top-down search. So you start out with something that matches everywhere, and you make it more and more specific over time. Specifically here, we're looking at this expansion where we look at, OK, we've got something that's a plus, and then it matches at 2 different locations, right? So this matches at a variety of locations in the corpus, these 5 specifically. We can do stuff like freeze and say that, OK, this left variable, that'll just stay a variable. We can also expand even in subterms. So here we're saying that the right side has to be something multiplied by something. And again, it matches at the same set of locations in the corpus in this particular case. We can continue to expand. Some of our expansions expand our abstraction without actually making it bigger. So in this case, it's putting in a 2 for that leaf on the left of the times. And that expands how much we're explaining about the corpus at each match location, but it's not actually increasing the size of the abstraction. And here, again, it keeps the same set of match locations. And we can finally get a completed abstraction by freezing the last variable. And we end up with something here that actually does compress the corpus. So the original size of the corpus was 35, but if you rewrite using this, it brings the size down to 25. And if you add back in the abstraction cost, that only brings us back up to 30. So we've successfully compressed the corpus at least somewhat. Now, of course, I just showed you the path to the optimum, but there's many other paths you could take. So from this second one, we could instead expand the left side and say, oh, that's a 2. And that would only match at one location, but we can continue from here, and we can continue expanding. But wait, is this search path even fruitful at all? Well, one thing we can notice is that at any future point, we only have this one match location, or potentially fewer, right? As you expand out your abstraction, you can never gain more match locations because you're just making your filter of what locations apply more and more specific. And at this match location, we can only save 5 nodes because the match location only has 5 nodes in it. So the lower bound on the cost of the rewritten corpus at this search path is in fact 30, right? So it's 35 minus 5 that we could take out, 30. So we can just prune this entire search path because no matter what, we'll never find anything better than what we've already found. And in general, the lower bound here is just the corpus size minus the size at each match location of the tree at that location. And in general, what we find is that lower bound means aggressive pruning. So this is the secret sauce that makes Stitch work. But there is a problem with Stitch. The main problem is that matching is purely syntactic. So let's take that corpus we had before that was very nicely structured. You might have noticed everything matched, and make it a little bit less nice. Let's commute some parts of this corpus, right? So we're going to commute these plus nodes, and we're going to commute these times nodes, or this one times node. And this is, of course, equivalent semantically to the original one under some very simple set of DSRs. And however, when we run Stitch, exactly the same process as before. It starts out all the same, but then when we try to expand to a times on the right child, we end up with only 3 matches instead of 5. And then when we expand to a 2 on the left child of the times, we end up with only 2 matches. And when we eventually get our final abstraction, the overall cost ends up being 36, higher than what we started with. So not only did we not find 3 of these matches, this entire abstraction will just not be found, despite the corpus being semantically equivalent to the one we started with. So this is obviously a significant limitation of this approach. So that brings us to our approach, which is effectively just running the same kind of a Stitch top-down algorithm, but over EGRAPHS and all the complications that arise when you try to do that. I'm not going to go over a very complicated big picture of this because you've just seen the algorithm. It's more or less the same approach, except when we run into, obviously, an E-class that has multiple E-nodes in it, because then you can match in multiple ways. So effectively here, take this E-class, which has 2 different plus nodes because it's commutative. And the 2 children are square root of something and 2. And when we apply our expansion to this, we match in 2 different ways, right? We can match in one way where the left child of the plus is the left child in the original corpus, the square root, and the right child is 2. And we can also apply in the opposite way, where the left child is the 2 and the right child is the square root. Now, I've shown 2 copies of the eGraph here, but crucially, we're not actually duplicating anything. We've just got these 2 different matches that we're tracking. And in fact, we're not tracking them for very long. If we freeze the left child of our abstraction to 2, we immediately drop one of these matches. So we don't actually have to keep this bookkeeping for very long. And once we eventually freeze that last variable and expand it all out, we end up matching at this particular node, which in the original corpus would have been in the opposite order. So original Stitch would not have caught it. And one thing to note is that we never had to think about the fact that this lower this lower E-class had 2 different ways of matching. So this is what allows us to handle cycles and stuff pretty natively. We only have to care about the actual multiple matches at the locations that are variables within our pattern. And one other thing, I'm not getting into the details here, it's a little technical, but we also do try to make all of our matches kind of Cartesian. So if there's multiple different variables that could match in different ways, but that are kind of orthogonal, we don't actually store the entire list of possible ways to match. So yeah, there's several interesting things, interesting to me, things that we did to try to make this work over eGraphs. Stitch doesn't just work out of the box, but I was told that they are only interesting to me. So I'm going to talk about one thing here, which I think should be interesting to everyone, which is a better lower bound. So I was emphasizing how amazing the Stitch lower bound is, but it doesn't really work for eGraphs. It works well on corpuses, and you can kind of think of it as like the average size of a match times the number of matches. And really, the benefit comes from the fact that if you don't have very many matches, you have a very bad lower bound, right? So that's what you're subtracting out, so you end up with not that much savings. The issue here is that on eGraphs, there's a huge number of complications that arise. First of all, you can have multiple matches at the same E-class, as we showed earlier. So if you've got multiple matches at the same E-class of your pattern, then how do you handle that? Now, there you could say, OK, well, just take kind of the minimum lower bound over the different ways you could match at a given location. The other problem is that you could have E-classes that appear multiple times in the minimal term, and you're matching at those locations. So how do you handle that? Again, you can generally handle this with a bit of bookkeeping. However, the real thing that will bite you is that some E-classes might appear nowhere in the minimal term because they're just not optimal for that particular location. And if you've got a match there, it might not appear anywhere in the original term originally, but then when you compress it, it might start appearing in the original term. So you kind of need to handle all of that kind of dynamism. So that brings us to our better lower bound. For this, we're going to go over a simple example. So the idea here is that we've got some root node f, and it's got two children. And these E-classes have the minimal term f of this G term and then the H term. Those are the minimal terms for each of those individual E-classes. And then we've also got this much heavier plus term here. What we've got is a pattern that matches at these subnodes of that plus term. And it's completely useless. There's no situation in which this will ever be compressive because it's already frozen the 1 and the 2. So it'll just never be able to do any significant compression on these particular locations. The Stitch lower bound would start by saying, OK, well, each of these subterms where it's matching costs 4. So we could save up to 4 at each location. Therefore, the lower bound is 7 minus 8, because of each of the 4s, is -1. Now, -1 is not a particularly tight bound on the overall cost of this particular rewritten corpus, right? So what we would really like to do is something that's a little bit tighter of a bound. Now, one thing we can do is just say, well, what if we just did the same thing, but we actually took into account the fact that we're in an eGraph? So we replace the roots with 0. It's basically the same thing. But instead of just assuming that that's going to linearly reduce our cost, we do a bottom-up traversal and recost each of the nodes. So we can then say that these E-classes above are 2, and then the ones above that are 5, or the one above that is 5. And you might recognize this as just the normal computation for the size of the minimal term on an eGraph. And we get the much more reasonable lower bound of 5. The thing is, once we're doing all this work, we might as well do something a little bit more sophisticated, which is to note that we're not actually ever going to be able to rewrite a particular node to 0 cost, right? First of all, the actual function call has some cost, right? You need to put the function symbol in. But then also, we've committed to not expanding the 0 and 1. So those inputs will just have to be inlined in there, right? So we've got this fn1, 2 on the left child, and we've got this fnab on the right child, and potentially more variables, but we don't know those yet. So we'll approximate this, or sorry, not approximate, we'll lower bound this with a 3 at each location. And then if we bubble this same thing up, we end up with a lower bound of 7, which is exactly what the corpus cost originally. So in fact, this new bound realizes that our abstraction and any follow-up abstractions, any expansions of it, are totally useless. So we can prune this tree. And this is true even if we didn't have anything to compare it to. So you might have been thinking, OK, well, this has some advantages, but it seems a little complicated. The advantages are, of course, that it's far tighter than the Stitch lower bound. And the other one is that it quickly grows as we freeze variables. These are both advantages that apply even in the situation where you don't have an eGraph and we're just operating over a tree. However, there is one significant disadvantage, which is that it's way more expensive to compute. And we'll get into some of that when I get into the results. And now for some algorithms. So how do we actually do this top-down search? One algorithm, this is kind of similar to Stitch, is that we maintain a frontier of nodes that are each node is one of these abstractions, and we just pick the best node at every time. We score it based on the cost so far, and we expand it. And this is eventually exhaustive, so it will find the optimum eventually if you run it for long enough. And the main downside to it is that symmetries mean redundant paths. In other words, if you've got like a plus AB pattern somewhere and you've got a plus BA pattern, then you're going to have to explore both of them to some degree. Maybe you'll be able to prune one with a lower bound, but if you can't, you just kind of have to like look at both of these, and they're kind of redundant. On the other hand, we also use sequential Monte Carlo, and here we keep a set of particles. Each particle corresponds to one of the abstractions, and you expand each one randomly, and then you reweight them based on the cost. Now, the main downside to this approach is that it's non-exhaustive. Technically, of course, sequential Monte Carlo is exhaustive if you have an infinite number of particles, but my computer is finite. The main benefit, though, is that it is completely insensitive to symmetries. So if you've got a plus BA and you've got a plus AB pattern, and you're evolving them over time, you just have both. And it's not a big deal, because they're just both weighted equally as particles within your search. And you might just pick one or the other, and it doesn't matter. So just to get into what sequential Monte Carlo is to some degree, we start with some particles. Each of these represents an abstraction. We expand it. That's one of those expansions we saw earlier. You then reweight these particles based on the cost function, and you divide that by some temperature. You take the exponent of it. And then you resample the particles, and then you, of course, repeat this process over and over again until you find something good. And now, finally, for some experimental results. Now, I've been talking this entire time, of course, about the need to run these algorithms over eGraphs, but you can run these over eGraphs that just don't have any rewrite rules in them. So that effectively, this is a comparison on what they do in program trees. And what you find here is that we compare to both Babble and Stitch. Babble doesn't do particularly well here. It's not really what it's intended for. But you can see that Stitch gets optimal performance, kind of by construction, and so do we. We get kind of very similar performance. In terms of time, we only have an overhead of about 2x. So that's all the eGraph tracking and everything like that. Doesn't add all that much to the cost of the search. And we're even a little bit better than Stitch on a couple domains that have a very large number of nodes in them. So that's the first two domains. That's because of our lower bound being a little bit stronger than Stitch's, even though it's a little slower to compute. Now, of course, primarily we're interested in domains that do have rewrites. Stitch drops out here because it just can't handle them. And our comparison is mainly to Babble. And in our comparison with Babble, we find that we're able to improve compression a little bit. So we go from 4.06 on Babble, we're able to get 4.85 on average across these domains. But more importantly, the time reduces considerably. So Babble takes about a minute on average across these domains, and we're able to do it in 2.6 seconds. However, these rewrites, which are the ones from the original Babble evaluation, are not as powerful as we'd like, and we have some other ones that are potentially a better direct comparison between our technique. So that brings us to this new molecule benchmark. The idea here is that molecules are often trees. So for example, alcohols are often trees. And they can be represented as programs, right? They're graphs, but they're tree-structured graphs. One thing about this, though, is that they're undirected graphs. And there's multiple isomorphic representations as programs of these graphs. And so we want to be able to handle kind of extraction of features on these. And molecules in a family have some common structure associated with them. And we want to be able to find that. Now, of course, chemists have solved this problem. They've solved it with this very complicated system of very specific ways of writing molecules down. Effectively, you can think about it as a kind of canonical graph representation. It's called SMILES. But what we would like to do is be able to get the same kind of compression and the same structure finding without any domain-specific knowledge. All we're putting into this is the fact that there are symmetries and tree rotations and stuff like that, like basic stuff that anyone would know. And the baseline here is, in effect, Stitch applied to the eGraphs min term. We're doing this because throwing stuff into an eGraph and finding the minimal term itself does canonicalization. for you. So we just want to make sure that we're actually getting advantage from searching over an eGraph rather than just from the eGraph existing in the first place. So that leads us to our molecule results. What we find here is that first of all, this BFS at start baseline is what I was just mentioning, and in general, it does not do as well. It only gets about 3.6, whereas we're able to get something like 4.7 to 4.8, so we're able to get significantly more structure. And the other thing that's probably that's important to note is that we still produce a strong improvement over Babble, which takes much longer and in some cases runs out of memory before being able to solve this problem. Another thing to note here, and I should have put this on the slide, but another thing to note here is that in the previous examples, you might have been wondering, why even bring up the sequential Monte Carlo algorithm? It's not the optimal one. And here you can see why. It's actually much more helpful when the rewrites are more powerful. It's able to find better compression in less time than the exhaustive search. And just for some interesting, pretty pictures here, what you can see is that on one of these examples, we're able to find up here this abstraction that kind of represents this molecular structure that just was not able to be found by the algorithm that's just running a regular search over the minimal term. And some other ones here. I can go back to these later if you'd like. And yeah, so in summary, we've got a couple things that we left out of this presentation. So we handled the Brown indices specially. We adapt a bunch of the pruning rules from Stitch. And we prove the soundness and completeness of our technique. None of that was in this presentation, but it all exists. We also have a few questions for you. One of them was, we represent ways of matching as a Cartesian product over variables. I don't know if anyone here is working on something relevant or knows of anything relevant there, but that seemed like something that improved things a lot in some cases. And the other thing is, do any of you think that there are any benchmarks that would benefit from more scalable eGraph abstraction discovery? And yeah, I'll just leave the summary on here while we take some questions.
Okay, thank you very much. We have time for a question or two.
Okay, so it looks like a stage is a kind of greedy process. You extract one abstraction at one time, and then you extract the next. So is there a phase ordering problem here, or there isn't? So
there is, yes.
Okay.
We're not currently treating that as in scope, but I think that our stochastic approach probably would be able to solve this if you then layered on top of beam search, or if you then layered on top of it just more sequential Monte Carlo.
Thank you.
Okay.
Yep.
Then we'll leave it there. Thank you so much.